Connaissance,
Recherche,
sciences,
et sciences mathématiques,
théorie,
physique, philosophie,
conférence,
archéologie,
environnement,
nature.
Okay. So good afternoon, ladies and gentlemen. As most of the picture I will show you are graphs with numbers. I don't have many beautiful pictures, so I selected some just for entertainment. So we stay on this now, and I just need a laser. You have. This is a laser? Oh, yes, okay. So let's stay on this and on thermoregulation, but this time we will I will show you the use of an approach that is more quantitative. So to start with a very original introduction, since there are discoveries and for many years, dinosaurs and many Mesozoic reptiles were considered as very traditional reptiles, which were cold-blooded animals, spending most of their time lying on the ground and basking in the sun. And here, in this very old reconstruction, you can see some dinosaurs, some marine reptiles, all together with turtles, with pterosaurs, and so on. And so, from this interpretation of this Mesozoic faunas, it was assumed that this animal lived under warm and equable climates. Equable means that with very low seasonality. And the fact that we found these reptiles on everywhere in many continents and even in high latitudes areas suggested that all over the Earth the climate was warm. But with the development of stable isotopes, it was shown that actually during the Mesozoic, the climate were not so warm and so stable as previously suspected. Here, I will show you just a few examples. Here, in the marine realm, you have here the temporal variation of sea surface temperature estimated from the delta weighting values of fish teeth, all recovered from the western Tethys realm. And as you can see, during this part of the Jurassic and Cretaceous, you have period of very warm period, and also some very cold intervals. And if you look at in the terrestrial climates, here you have the latitude equatorial areas to polar areas, and here mean air temperature reconstructed from the oxygen isotope composition, this time of continental vertebrates. You can see, compared to the present-day latitudinal temperature gradient, that during some parts of the Cretaceous, here you have the late Cretaceous, and here the early Cretaceous, sometimes around the Aptian, temperature in medium to high latitude were not so warm, and they could be also at very high latitude near freezing to freezing, especially during the early Cretaceous. So if we look at the distribution of vertebrate taxa at high latitude, here you have this representation that was published in Science in 2002. You can see that among mammals, birds, pterosaurs, and very, very few reptiles, you have a very huge diversity of dinosaurs. So let's ask again this century-old question. These dinosaurs, were they warm-blooded, which means did they produce and regulate high temperature, body temperature, like mammals and birds do today? Or were they endothermic and homeothermic? Or were they cold-blooded, like a lot of extant vertebrates and reptiles? So, to answer this question from a quantitative point of view, there is one possible method is to use isotopic thermometer, which is the oxygen isotope composition of apatite phosphate that you have here. So, from a general point of view, when apatite precipitates from an aqueous solution with delta-weighting values, there is a fractionation, oxygen isotope fractionation, that is dependent on temperature of the solution. So if we apply it to vertebrates, this delta-weighting value of phosphate that is produced by that make up teeth, bones, and scales for some fish. It will depend on the delta weighting values of the body water from which it precipitates, and which reflect, of course, ingested water and some life traits of the animal, and also body temperature. So for homeotherms animal, this is a constant values, and for poikilotherm, these values depends on environmental temperature. So let's take an example first. If from these two lovers, if we take from each one a tooth, here you have a mammal, a gnu, which body temperature is about 37 degrees, and this crocodile will has a body temperature that is very depends on environmental temperature. If we measure the delta weighting values of phosphate from these teeth, we will have a difference between the two, and part of this difference will correspond to the difference in body temperature. So this is the basics of how to use this thermometer. So let's go to the application. So the first try to infer dinosaur thermophysiology or body temperature was made in 1994 by Rhys Barrick and Bill Showers, who used the following approach, considering they considered the fact that an ectothermic animal may encounter local heterothermy. It means that, meaning that from the inner core and the extremities of its bodies, it will undergo there will be some difference in temperature. So by analyzing oxygen isotope composition of bones from close to the main core where there is most heat, and from distal part, if Tyrannosaurus rex was homeothermic, there would be very few temperature variation. And if he was poikilothermic, there should be some huge temperature variation. And what he found is that he found some temperature variation, but that did not exceed 4 degrees compared from the tip of the tail compared with the dorsal vertebrae. And from this, they concluded that it's not so big variation, so Tyrannosaurus may have been a warm-blooded animal. However, this result was highly criticized, first for a preservational point of view, because they analyzed bone, oxygen isotope from bone, who are more sensitive to diagenetic alteration than other more mineralized tissues, such as dentine or enamel. And secondly, also, and this will be illustrated by this work from 2001. If you look at today's American alligator, a similar work was performed, and on similar bones. And as you can see, temperature variation do not exceed 2 degrees, which is even lower than for this tyrannosaur. So it's totally depend also on the environment where this dinosaur lived. So maybe it was warm enough for the dinosaur just to be able to keep constant temperature throughout his body. So it was nice try, but there was since another approach that was proposed. I will call it the latitudinal comparison approach, and it's based on the use this time of the Earth surface properties that, according to latitude, the paleotemperature decrease from equatorial region to polar region, and also, of course, the delta weighting values of rainwater, which we call here meteoric water, it decreases altogether, yes, with decrease in temperature. And if we build a basic framework, an endothermic animal will have a delta weighting value variation with latitude here that you have in ordinate that will just follow the variation of the meteoric water, which is drinking water. Whereas the ectothermic animal will both, its delta weighting values will both reflect the variation of its drinking water, but also the mean air temperature of its living environments. So the two curves will be different. So keeping this in mind, in 2000, Freaky and Rogers did this work, and they compared theropod delta weighting values with crocodiles in some localities of various paleolatitudes, and what they found is a difference in slope between these two animals that mimics this model I just show you. So what they demonstrate is that the sister group of birds, theropod dinosaur, were warm-blooded animals. So the question was, how about the other groups of dinosaurs? And I had the opportunity during my PhD thesis to try this method on these 4 groups of dinosaurs, so theropod, sauropod, ceratopsian, and ornithopods, coming from localities of different Cretaceous age. And for each layer where I sampled dinosaurs, I compared them with crocodilians and turtles. And so here is another way to express this difference. Here you have the delta weighting values of dinosaur minus delta weighting values of non-dinosaur reptiles, and here absolute latitude. And so here is the modern framework. This curve corresponds to the difference between today an endotherm animal, so with a body temperature of 37 plus or minus 2 degrees, minus a pure ectotherm, so whose body temperature will change with changing latitudes. So, and here, in this framework here, is if dinosaurs are ectothermic animals, then the difference between them and crocodiles and turtles will follow a straight line. If dinosaurs are warm-blooded animals, these different groups, then it will follow this curve. So here is the result, this point, and here you have the regression and the 95% interval belt to the data distribution. And as you can see here, this curve is statistically not different from the modern curve of endotherm minus ectotherm. So this provides good evidence that dinosaurs were homeotherms, because their delta rating values reflect meteoric water values only, whereas the delta rating values of crocodiles and turtles both reflected the drinking water and environmental temperature. And they were also, I think, they were also endothermic, because for the two reasons, the estimated body temperature of dinosaurs made using this theoretical framework are in the range 35 to 39 degrees. So it was above air temperature in high latitudes, or anywhere actually, because 35 degrees is quite very high. And also the two samples I got from high paleolatitude belongs to small size individual, maybe 1 meter, 2 meters, 3 meters long. So this precludes the gigantothermy as an explanation of their body temperature. So if we look back at this distribution map, we can see that there is also some other reptiles that lived at high latitudes, which are some great marine reptiles, some plesiosaur, mosasaur, and there is no picture about it, but from Spitsbergen there is also high ichthyosaurs. So let's ask again the question, were they warm-blooded or cold-blooded animals? And for this, just to tell you that it's exactly the same in the marine realm. Marine endotherms have a delta rating values that only reflect the value of seawater, whereas marine ectotherms, such as most fish, have a delta rating values that both reflect the delta rating values of seawater and, of course, seawater temperature. So let's draw the theoretical framework here. So to express this, I will use a similar way, which is here in ordinates. You have the delta rating value of the reptiles minus delta rating values of fish that will be used as the ectotherm for comparison. And on the abscissa here, you have the delta rating values of fish phosphate that directly reflect seawater temperature. Higher delta rating values corresponding to lower temperature. So first, if tested reptiles were ectothermic animals, then we would have a line with a null slope. If this reptile were endothermic, for a seawater value of 0 per mil, which is the modern seawater value, oxygen isotope value, we would have this. The values of this data would be encompassed between these two lines, these two blue lines, for an animal between 35 and 39 degrees, and we would have a slope of -1. Also, from this model, I use body water of potential marine reptile to be equal as the seawater delta rating values plus 2 per mil, because it has been shown in modern breathing aquatic vertebrate that the drinking water, the environmental water they drink is enriched by up to 2 per mil when it's become body water. So this is a theoretical framework. Of course, this model is for modern seawater, but we know that even during Jurassic and Cretaceous, or maybe Triassic, the ice sheets, the polar ice sheets, had some growing and decaying events. So the real value of delta rating, the real delta rating values of seawater have fluctuated between -1 and 0 per mil about. So this is here the complete framework, just which we will use, yes, to test our data. So here I represent here a temperature scale. These are values if seawater values is -1, then these fish values would indicate temperature from 14 to 30 degrees. And if we have modern seawater values, this scale would start at 18 degrees to 34 degrees. So what we did was to, in each sedimentary layer, was to compare the delta 18 values of one of these 3 marine reptiles and coexisting fish that came from many localities spanning from the Triassic to the late Cretaceous. And what we got for ichthyosaur is here and a slope of more than -1, a very steep slope. For plesiosaur, the slope was around -1, but as you can see, the value distribution is more grouped, so it's not. So the data can be discussed. And finally, for mosasaur, we have a flattened slope of -0.7. So if we put all this data all together in this framework, what we see is that they all fit within the -1, the global -1 slope, and within values expected for warm-blooded marine animals. So we can say that these marine reptiles were homeothermic animals because they have the slope of the data distribution is close to or equal for some to -1. So it means that their body temperature was constant, whatever the temperature of their environmental water was. It's okay, I think it's end of time. And also, they were endothermic animals because they had body temperature higher than temperature of their environment, and considering the heat capacity of water, internal heat production only could keep body temperature above seawater temperature 1. So for this case, again, gigantothermy is unlikely. So I will stop here. I will stop here by asking a question to this assembly, because there was a comment from this paper from Motani, and is for him the difference of slope. We also proposed it, but for him it's something very strong. We have a steep slope for ichthyosaur that are large, fast cruiser, and a flattened slope for plesiosaur, and even flattened from mosasaur. And what was proposed is that it fits very well with the speed of these different animals. And so the question I ask here is, do we have to find, is it relevant now to just look at the origin of endothermy from a phylogenetic point of view? Or is it maybe many other groups may have developed this kind of temperature regulation? So I will stop here by saying now Mesozoic was not a warm world with cold-blooded animals, but could have been a cold world with one dominated by warm-blooded reptiles. Thank you very much for your attention.